Okay, so next unit, um, schedule this week about the labs. There's lab 9. There's a question at the back end of lab 9 that we'll talk about kind of in the middle of this lecture. But otherwise, lab 9 is going to be about the output analyzer. So now that we've talked about, we're starting to talk about stats that we're using to summarize results from simulation. The output analyzer is a tool the Arena gives you to take DAT files out of Arena and then pull apart those stats so that you can get access to them without having to write your own output frameworks that you have to process in Excel and so on. So that's what Lab 9 is going to give you practice with. And then in Lab 10, you get some more advanced tools. So the big thing about Lab 10 is to learn about tools that make it easy to automate experiments. So if you, let's say you've got your final project and you want to figure out like, well, if I've got a number of kiosks that I've installed at this bank and I want to test it at 2 kiosks, 4 kiosks, and 6 kiosks. So you can have a parameter in your sim, which will be the number of kiosks, and you can have the process analyzer automatically run experiments at each one of these levels. So you don't have to build 3 different models. You have one model with the parameter, and the process analyzer changes that parameter for you, kind of like behavior space. And so you'll get an opportunity to play with that in Lab 10. Lab 10 also has a bunch of bonus credit on it so that we can learn about like batching and things like that. Of course, you can choose not to do it. But if you do everything in Lab 10, then it's an opportunity to get, I think, 50 points out of 30. So it's almost allowing you to excuse another whole lab by doing all of Lab 10. So, and then that's the last lab. So then the last 2 spots that would normally be for labs are to make sure you have enough time to finish up your final project. So your final project, I'm moving through the input modeling report. So hopefully you get feedback from that soon. I might just start releasing feedback as I grade rather than waiting to release them all at once just to get that back sooner. And then the next deliverables are in the final week of classes. And so your presentation video and your final report are both due the Wednesday of the last full week of classes before finals week. Wednesday, so that then there's a couple days left of that week for you to do your peer reviews. And so every individual will have to review 1 video of another group and 1 report of another group. And then those peer reviews come in, and the peer review scores plus my scores help collectively determine the grade that the groups will get. So those won't be presented in class. Those will be uploaded to Canvas. And so you only have to watch 1 and read 1. So it's not like everybody has to watch everybody's or anything like that. And then your peer reviews will be due the Saturday before finals week. And again, there's 2 of them there, 1 report and 1 a presentation. So that's the plan here. Other assignments, we've got these ICAs, a few left here. So I think 2 normal ICAs before the final exam review ICA. Then homework H, it'll be due soon. I think you now have all the info you need for homework H. And then the last homework will be homework J2. That's an assignment which, again, I've said this before, unlike the other homeworks, it is not one that can be dropped. And so you get to automatically drop your lowest homework except this one, because we collect ABET metrics. So everybody's got, or at least have to assess everybody on it. So please try to complete that homework. It is an arena-based homework, kind of merges lecture and lab topics together to be kind of, again, this tool to help us capture what you've gotten from both halves of the course. All right, any questions? Okay. Last time we talked a lot about the ROC curve, the ROC curve, and how it comes from this graph up here, and then this alpha, beta, and power relationship. So we talked about where the t-test comes from. Key things to remember there is if you're ever going to use a t-test, the terminology we use. So the number of averages you're averaging from your data is the number of samples in the t-test. So 1 sample t-test means you have 1 population that you are averaging and then testing against a hypothesis. A 2 sample t-test is you've got two populations and you're testing whether they have equivalent means to each other. So that's the one sample versus two sample. If you use a t-test, the data you're collecting have to be normally distributed. So in this class, I'm not forcing you to do this, but normally you would have to do a test of normality. I've mentioned a couple of test normalities, but you have to test that first. And then after that, then if you've also got an experimental design where you're sure that these things are independent of each other, then you can move forward with the t-test. So those are important constraints to think about with the t-test. The t-test, we talked about where it comes from, is that under those assumptions, if you have a small number of samples going into that average that's in that numerator, then we can set up something that's analogous to the standard normal distribution, but it works for a low number of samples as well. And that's this t-distribution that's up here. And so you can see the t-distribution looks more and more like a normal distribution as the number of samples or degrees of freedom goes up. So really, it's once you have like more than like 30 samples, you can just treat it like a standard normal. You can almost forget how many samples you have. But under 30 samples, that's where the t-test really shines. And that's what it's kind of there for. It's to enable your experimental designs with few numbers of replicates, because replicates are expensive. So we don't want to always have to rely on having hundreds of replicates. We'd like to be able to do it with 10 if we can. So if we only have the budget for 10 replications of our experiment, how do we statistically test whether the mean that we get out of our data matches up or mismatches from a hypothetical mean? Well, that's what the t-test gives us. That's the idea there. Along with the one sample, two sample, there's also one-tailed, two-tailed. The one-tailed here says that if you saw deviations from your hypothesis in one direction, you'd want to flag that as a detection, but in another direction, you wouldn't care. And it's very, very rare that is an appropriate approach. A lot of times when you see people use a one-tailed test, it looks like they didn't have enough data to achieve significance, but they really had wanted to make a detection, and it's easier to make detections with a one-tailed test. So unless you have really strong justification for why you wouldn't care about deviations in one direction, you only care about them in the other, then you always do a two-tailed test. So that's why we always look up in the back of the book, whatever your significance level is divided by 2. Because the back of the book, it's just easiest for them to give the one-tailed test numbers, critical values. But because we do a two-tailed test, then we want to make sure that we chop the little bits of the tail off on the one-tailed, because we're going to add them in on the other side. And that's why we cut that alpha in half. So that's where that comes from. So those are the fundamentals of that t-test. I mentioned that as you increase your number of samples, what it does to this so-called pivotal quantity is that it adds space between your standard hypothesis and a hypothetical one that has the same variance, but a potentially different mean. So I have this little example I just wrote up in MATLAB here, where this blue curve, that is the t statistic for 4 samples, where the real population had a standard deviation of 2. And then I've got an alternative hypothesis that also has a standard deviation of 2. So they're both normally distributed. And but this one's got a higher mean. So this one's got a mean that is 2 more than this mean here. When I calculate the t statistic for both the actual distribution and the alternative distribution, the actual distribution falls exactly where we'd expect the t-statistic to fall, on 0. But then the alternative one that's been shifted over by 2, it gets shifted over by, it happens to look like a little bit, like it's close to 2 in this particular case, that's just coincidence, but it gets shifted over by this amount. And so right now we see this amount of ambiguity. So if I were to get and if I were to take a bunch of data and average it and say, is it from the blue distribution or the red distribution? If my average showed up right here in the middle, around 1 or so, it would be very difficult to tell the difference between, that could be just as likely to come from the blue distribution as the red distribution. So if I were to say it's from the alternative, then it is very likely that I'd make a false positive. But it's also not so great if I say, oh, it's got to be from the blue distribution. I might also be making a false negative because there's just a lot of ambiguity there. So what happens when you increase the number of samples, it not only does it change the shape of these t distributions to make them higher and the tails narrower, but it separates the alternative hypothesis. So this is the same alternative hypothesis here, the same alternative generator. It's just has a unit 2 mean difference. But it's been now in t space, it's been shifted over where now it's closer to 5 here. So I've now separated them out. So now there are fewer overlaps between the t distribution from the hypothesis and the t distribution from the alternative for this effect size. And so if I keep doing that, so I now have 30 samples. So up here, it tells me how many 30 samples. So if I go back here, you see this was 20 samples. If I go back here, this is 4 samples. So if I go forward, this is 30 samples. It's separated even farther, but there's hardly any overlap among them. So that's when we say you get more statistical power. What you're doing is you're creating daylight between your alternative distribution and your hypothetical distribution. So under the null hypothesis, these are the values I would get. If I happen to instead generate values from this alternative hypothesis, it's going to be very far away from the null hypothesis. And that's the magic of extra sampling, is it pushes the alternatives away from the nulls. And that is what gives you more power. And that is one way to do that, is just by increasing the samples. But another way to do that is by decreasing the standard deviation, decreasing the variance in your experiment. And that's going to become a major part, not of this unit, but of the next unit. But we start flirting with that idea in this unit. And we've already sort of started to do that with the homework. And so, so here I've got the same 30 samples in the previous slide, but I've managed to create less variation in the outputs of my experiment. Now you say, well, how do I do that? It's just, that seems like that's asking for too much. It seems like that's magical because I'm sampling from a system and the system's variance is whatever the variance is. But in our experiment, when we're setting up the experiment, there's ways in which we can control for. So the word control in statistics means account for variance. So when I say I control for something, when I design an experiment, what I'm doing is I'm saying that I realize that a certain part of the variance of my output is due to something that I can measure or control. I can actually change the values of. And if I can measure or force the values to be what I need them to be, then I will reduce the effective variance on the output. And by doing that, it also creates more daylight between the null distribution of my t distribution and a t distribution if my null was false. And so that is sort of hinting at this example that we did that is like the example you see in the second problem of your homework right now, where you do this paired. So you've got, instead of generating random data with your sim and comparing it to data generated in the real world. So we want to say, is my simulation output similar to my real world output? Well, I could just generate customers in the sim that are statistically similar but different than the customers in the real world. But that introduces variance because I might happen to generate a lucky set of customers for the system in my sim, and an unlucky set of customers will be out in the real world. So in order to decrease the variance in my output, I give both simulation and real world the same customers. Now, of course, I can't generate fake customers here and pipe them into the real world. That's impossible. But if I have data on the real world customers, I can then generate customers in sim that are identical to the customers in the real world. And by using the same customers in both systems, then I eliminate the source of variance that just comes from there being different populations of inputs here and different populations of inputs there. So that's one of these examples of how we can cleverly design our experiments to reduce variance. And if we can reduce variance, we may not have to increase replications. And that is not the major focus of this unit, but that will be the major focus of the next unit is how do we, instead of increasing the number of replications, how do we cleverly change the experiment so the same number of replications ends up giving us more power? And so we did that, like I said, in this example that you do in your homework, same input data, historical input data in both systems. So you now are going to do, instead of a two sample t-test, two populations. So it used to be, before I'd use the same customers, I had a population of customers, and so a population of outputs in the real world, and I had a population of outputs in the sim world. And those are two populations, two different averages, two sample t-tests. But now that I've linked them together, then I have, for this set of customers, it runs on both systems, and I get one difference in performance. For the next set of customers, runs on both systems, I get another difference in performance. Now I just have one population of differences. And my question is, are those differences close to zero, which would mean the systems are the same, or are those differences significantly different from zero, which means the systems are different? And now that I'm using a single population of differences, I use a one sample t-test. And when you hear about a paired difference t-test, that's all it is. It's not a new t-test. It's just saying, I'm going to take your two populations, you're going to tell me how they're ordered, and they must have the same number of elements in that population as that population. In a two sample t-test, you could have 10 replications here and 20 replications there. It doesn't matter. But in a paired difference t-test, you're saying I have the exact same number of replications in that population and in that population, and I have a way to pair them so that the first replication there goes to the first replication here, second to second, third to third, and so on. And if you have that mechanism, that experimental design, you get a single population of differences that you just run a one sample t-test on. And that's what a paired difference t-test is. It's just doing all of that for you so you can get a normal one sample t-test out. And then we know how to do a power analysis with a one sample t-test. You can do power analyses with all sorts of other tests. They're just a little more complicated. There are special tools that you can buy, like G star power, for example, is one of these tools that will do power analyses for all sorts of tests. Sometimes in order to do a power analysis, you have to do a simulation study. You actually have to generate those alternative hypotheses, like I did with MATLAB there, over a wide range of alternative hypotheses, and then it'll calculate your power for you. So in this class, I want you to know what a power analysis is. I want you to know, for the very simplest case, how to do one by hand, so you know all the components you need. It's like, I don't want you to be able to bake every cake, but I want to you to be able to bake the simplest cake possible, so you know about things that need to rise and things that need to bake and so on. So this is the simplest cake possible. And then if you ever need a more sophisticated cake, you at least know what sort of ingredients you might need to get that are out there. But then you can pay someone else to actually bake it. And so most power analyses you're not going to do by hand, but you're going to need to know all the components that need to go into a power analysis. It will be the same as the simple power analysis, but there'll be a tool that allows you to take you over the finish line. So, this is the kind of problem you're going to do in that homework. You calculate differences. You end up calculating an average difference and a standard deviation or a variance for that difference. That will allow you to calculate what you need to do a one sample t-test. And in this particular problem, the focus is less on is this t-test going to detect a difference or not? It's sort of hinting that it hopefully will not detect a difference. And then the question will be this power analysis of, did I have enough samples so that if I did not detect a difference, then I can say, but my test is sensitive enough that if there was a difference that was big enough for you to care about, I would have detected it. So there must not be, therefore, a difference that is big enough for you to care about. So that's why in this test, I'm going to say that your stakeholder has told you that if your sim is different from the real world by more than 2 or something like that, then that's the difference I'm looking for. If it's less than 2, I don't care about it. So your test only has to be sensitive enough to see differences of 2 or larger. It does not have to be sensitive enough to see differences of less than 2. And that will help you figure out how many samples you need. And you'll do that by taking that desired sensitivity divided by the standard deviation that actually comes out of your experiment. That gives you this effect size. And then you go back to the back of the book and you'll look up these operating characteristic curves. And those will allow you to say, for what power do you want? Well, 80% power. Well, that's a 0.2 type 2 error. And for a delta of 1.5, that intersects around here. Now, if that happens on your homework, where it's in between these two lines, you're going to have to do a little bit of guesswork. I tried to engineer it so you don't have to do that much guesswork, but if it lands here, then I know that 7 is plenty, 5 is too few, so maybe it's 6. I would say in this case, if I were to position you there when I wrote that homework up, I would probably accept 6 or 7, because based on this graph, you really don't know if it's 6, and so it'd be totally reasonable to say 7, but 7's probably conservative because it sort of looks, 6, 7. So thanks for that. So that's my wife's gonna love that when that's how that might end up. Maybe it'll be easier, and if you get a delta of 1, well, that's very clear that it's 10 samples is what you need for 80% power. Any questions on the power analysis for the one sample t-test? All right, so you're ready for that homework then. Okay, so we talked about some terms last time that I want to make sure you know. So we talked about the t-tests, ANOVAs. These are all parametric tests. So these are tests that you have to make an assumption on your data, and you don't infer anything about the distributions because the assumptions fix the distributions. For a t-test, we can only do a t-test if we've committed to the idea that our data set are normally distributed. So at that point, what we're making an inference on is what the mean of that normal distribution is. So we're saying that my null hypothesis is the mean is 5, and I'm trying to detect the data that I got. I'm guaranteed there'll be normal, but I don't know what the mean is going to be. So for the data that I was sampled, is it possible that the mean is 5, like my null hypothesis is? And can I detect a difference from that? So we're detecting differences in our parameters, not in the distributions. That's why they're parametric tests. And if we can make these assumptions on these parametric tests, they give us a lot of power. They make the tests much more sensitive, but they only work if you can meet those assumptions. If you can't meet the assumptions, then we have non-parametric versions of the same tests. These are versions that do not make the assumptions on normality or whatever, and they test the same idea, but they're less sensitive. So when these tests come out with a p greater than 0.05, you don't have as much confidence that your null is in the ballpark. All you know is that you just couldn't detect a difference with a non-parametric test. And there are then, we didn't talk this about last time, but there are non-parametric tests that do make a couple of simplifying assumptions, but they're not assumptions on distribution. So like you can, for example, in the chi-squared test, we assume the expected value in each bin is 5 or more. That makes it a so-called non-exact test. So we made an approximation in the chi-squared test. So it is a non-exact, non-parametric test. There are other tests like the KS test. That is an exact non-parametric test because you make 0 assumptions whatsoever. It works for any data set where you want to do that type of test. And it's relatively high power too, which means it's very sensitive, so it'll detect these differences between that. So those are terms that I want you to know. You don't have to know all of the types of these tests because you can look them up. That's very similar to the cake analogy. I don't want you to know the ingredients. I know you want to know what types of ingredients, so that if you want to bake a more sophisticated cake, at least you'll know the general skeleton of it out there because you can look these things up. You can say, what is a non-parametric t-test? Google or Wikipedia. will tell you it's a U test. And then you're like, oh, that makes sense. TU, like U and T are right next to each other. But some of these other ones like ANOVA and Kruskal-Wallis, there's a lot of things that are named after people, so it's a little annoying. Eventually you memorize them, but at first you're just doing a lot of Googling. That's just natural. Okay, so parametric, non-parametric, exact, and non-exact. Any questions about that? Okay, so we talked about the chi-squared test last time. I'm going to just kind of want to show some demonstrations of, like we mentioned, the big thing was like, where does the 5 come for in the chi-squared test? And so let me demonstrate that a little bit differently than I did last time. So what I have here is a binomial distribution. So this, remember, it describes if you know the probability that an event is going to happen, this is how often that event will happen given a number of trials where it could or could not happen. So if you imagine this is a chi-squared test with 2 bins, then the binomial describes the count of the things in bin 1. And then bin 2 is it's whatever's left over, it's slack. So the 6-7 thing is still funny to me. Okay, but so up here, we've got this number of observations landing. Imagine that's landing in bin 1. And then so the expected count here is 5.5. Well, that's just saying that this probability, which is 5.5% times 100 trials, means that on average, I get 5.5 in this bin. Well, that means sometimes I get none in the bin. Sometimes I get a lot more in the bin. But that's our binomial distribution. This is the sort of exact test that we would use instead of the chi-squared test. But it is difficult for us to come up with a nice, clean chi-squared-like statistic when you have lots and lots of bins. So we look for an approximation of the binomial that lets us get there. And that approximation is the normal distribution, but that only works when the average is 5 or more. And so here is a binomial where the average in this bin is 1. And you can see that if you were to try to fit a normal to that, it truncates, like a bunch of the normal is just gone. So that's not a good approximation. You can go up. Here's 2 counts. It gets a little bit better. 3 counts a little bit better, but still you're cutting off most of the normal. 4, and then finally at 5, now this starts looking like a bell curve, where most of the bell curve seems to be captured by the normal. So there's not a lot of the normal that's left over in the negatives. And then once you get to 6 or higher, then the binomial looks very bell curve-like. So this is where that 5 comes from. If someone else says, it's like somebody's teaching 380 and they say like, oh, well, we'll do a 3 or whatever. If you set it lower, there's other things you have to do. And if they don't teach you those other things you have to do, then you're stuck with saying this is a normal. And this, there's a lot going on over here that is just completely chopped off here. So you really the chi-squared only works when this binomial looks like a normal, and a 5 is about the lowest we can go with that. So that's where that comes from. And once you have that, you can replace all of these distributions of counts in every bin with standard normals. And if you square those standard normals and add them together, then you get a nice little metric for how well you meet your desired distribution. So that's the idea here, is that if you've got the average value inside a bin is 5 or greater, then you can take the observed counts minus the average divided by this is in the normal approximation of a binomial, this is the variance in that approximation. And this z-score here will end up being a standard normal. It'll be distributed as a standard normal so long as the number of counts is 5 or greater. And so if I then square this z-score, I can now do a partial fraction expansion, and that's the chi-squared statistic. So that's the beauty of it. It's a sort of numerical trick, is that when you square a standard normal, you then end up getting this nice breakup here of the expected number of counts in one bin and its observed counts, so sort of the error from one bin and then the error from the other bin. It nicely breaks them up so you've got your two bins. And you can generalize that to as many bins as you want. So if you have 5 bins, what you're really doing is summing up 4 standard normals that are squared. And that's where we get this chi-squared statistic. So where do these curves come from? So these are the degrees of freedom for each one. So here, this one is 1 degree of freedom. Here's 2 degrees of freedom, and so on. What you're seeing here is if you took here this 1 degree of freedom, if you took a single standard normal, you went into MATLAB and you said draw random numbers from a standard normal, and it'll give you numbers from negative and negative and positive numbers, and then you square them. At that point, they're all positive. If you take that distribution, that's this ski slope here, this yellow ski slope. This green one, that one is you take numbers from one standard normal, and then you ask MATLAB for numbers from another standard normal. So it says draw a number from a standard, or draw a number from a standard normal distribution. It gives you one. And they say do that again, it gives you another. Square both of those so they're both positive and add them together. That gives you the green curve. And you can keep doing that. And by the way, that green curve, you said that looks kind of like an exponential. And it turns out that actually it is an exponential. That's one of the crazy things, is that a chi-squared with 2 degrees of freedom is identical to an exponential. And we can use that to generate all sorts of other random variables in more efficient ways. And that's kind of outside of the scope of this discussion, but it's not. It actually is an exponential there. So things come together at that. If you keep going and you say, well, now I'm going to take 3 standard normals, square them all and add them together, that's the distribution of this one down here, and so on and so forth. And that's why the chi-squared becomes more bell-shaped as the number of degrees of freedom goes up, because the chi-squared is just adding together more variables, more random variables. They happen to be squared standard normals, but over time, you're just adding together a bunch of independent random variables. And the central limit theorem says that if you add together a bunch of independent random variables, then eventually you get something that's bell-shaped. And so that's why the chi-squared eventually becomes itself a normal distribution with enough degrees of freedom. So the t-test becomes a normal distribution with enough degrees of freedom, the chi-squared, et cetera, et cetera. A lot of these stats are based on adding up differences from a null, which is why when you get enough degrees of freedom, enough sample points, they all just become normals. So we see that pattern over and over again. So that's where the chi-squared stuff comes from. And this is just emphasizing that as you increase the number of samples, then you get more tolerance for error. And so what that's basically saying is as you not increase number of samples, increase number of bins. So as you have more bins in your distribution, there's more opportunities for error. And so that's why the threshold that corresponds to p equals 0.05 will get larger and larger. So p equals 0.05 is like here somewhere. And if this is with a 2 bins, this is with 3 bins, 4 bins. As you get more and more bins, then the chi-squared threshold for p equals 0.05 gets bigger and bigger and bigger, because you have to tolerate more error, because you have more opportunities for error, because you have more bins, and every bin generates new error. So that's where the chi-squared test comes from. So biggest thing there is I just want you to have it in your soul that it really matters that 5 is your threshold for the expected count. And it's all because of this so-called continuity approximation, where you're approximating a binomial by a normal. Any questions about that? Okay. All right, so yeah, and I can generate these in MATLAB as well. So there's a chi-squared distribution, and then I generated a bunch of data from a distribution very close to that null hypothesis, and then one that's very far away. And I'm just sort of showing you this is the same idea. This is my null hypothesis. This is alternative 1, and this is alternative 2. And so you can see as the distributions get far away, then it becomes easier and easier to detect that, because there's less overlap between there. So if you end up getting data way out here, then it's nowhere near the null distribution. But if you get here, then there's a lot of overlap. And so again, that's just showing you the same picture I showed you with the t-test, but now with the chi-squared. Chi-squared, I guess, is different than the t-test in that you don't have to worry about the negatives. There's no such thing as a two-tailed chi-squared. You only can measure a positive difference from a distribution. There's no way to be like less than a distribution or more than a distribution. You can just be, I have a null distribution and I have a difference from the null. And that's what the chi-squared is measuring. So there's only one tail. Okay. Any questions about that? Chi-squared, feel good about it? The count test. Okay. So I already covered non-parametric. There's exact and non-exact. So chi-squared is non-exact. There are other non-exact tests that are a little, so like the G test, for example, that's a chi-squared test where the expected value that you need is less. There are these so-called continuity corrections that you can do before running a chi-squared test, which sometimes make it easier to run them with fewer expected counts, so less data, but they're very poor. So you try to avoid those. So that's why if you if you really need a weaker requirement for a chi-squared, the G test is an option. There are these exact tests which don't make any assumptions, and so they are often alternatives to the chi-squared. So a binomial test, I kind of hinted at that already. There's if you have more than two bins, there's a so-called multinomial test, which is like a chi-squared test, but with no assumptions. But it's the chi-squared test is more efficient for large samples. And that's why you still use the chi-squared test. There's something called the Fisher's exact test, but it can be a very low power. So there's all these trade-offs. So there are reasons why you select these things based on the assumptions you can make about your data. But you generally want to choose the highest power test you can with the assumptions that you can make about your data. That's generally the rule. This is why we have all these, is to help you when you don't have the assumptions, you have another place to go. It's not just to be pedantic and to have multiple ways to do the same thing. All of these tests have different pros and cons, and you have to select the one based on the assumptions you can make about your data. And that's something that's a little outside of the scope of this class. I'm okay with the next class if we stick to t-tests, ANOVAs, and chi-squared tests. But once you get out of this class, then you start doing other tests as well. Okay. So the KS test is an exact test. Where does its test statistic come from? How does it do its magic without making any assumptions about the distribution? And it basically, I'll just show this graphically. It does this thing called a Brownian bridge analysis. And so you have this red term is a cumulative distribution function of a distribution that you're treating as your null. And the blue is the sample CDF from sorting your data and plotting it against their rank. And you're measuring the difference between these. Well, this is what's called a Brownian bridge. And so what that means is you know where the bridge ends and you know where it starts. And so you know that in order to get across the bridge, you have to start in one place, you have to end in one place. But while you're on the bridge, you're allowed to walk kind of, anywhere you want on the bridge. You can kind of diverge and not. And so the question is, given that you eventually have to make it to like the exit point of the bridge, how far can you diverge and still make it back? That's where they get the distribution for the KS test. So it's this idea that if I have a Brownian noise, which is this thing here. So imagine I have something like this, where at every little sample point on the x-axis, you basically move up or down by a random amount. That will give you a trace that looks like this. If we consider only traces that start at 0 and end at 0 and have a fixed number of steps in between, so that's the number of sample points you have, then the question is, if you only have 5 steps to get from here to there, and you have to end at 0, you have to end at the end of the bridge and start at the start of the bridge, how far in the middle could you possibly get away and still be able to make it back to the end of the bridge? You can model that. So just knowing how many steps you have between the start of the bridge and the end of the bridge, and knowing that you take a little bit of a random move at every step to the left or the right, up or down, then you can model the distribution of, well, given that given that you made it home, how far away did you possibly get in the middle? And that's where the KS test statistic comes from. So it doesn't make any assumptions on the data set. It just sort of says, if I'm considering this CDF as a path home, that if you are from that distribution, you follow the path perfectly. But if you have a slight deviation from that distribution, then you might wander. You might be a little tipsy and wander off the path, but eventually you'll come back. And so, how far away can you wander from the path if you are actually from that distribution? If you end up walking a different path home, then you'll have a persistent distance, and that will be caught by the KS test. That's where it comes from. So there's all these different ways to come up with these statistics that help us measure these things. And I'm not going to go over how the rest of these work, but just know there are, you can dream up all these different ways, and the different choices you make as a test designer lead to different trade-offs. And so Anderson-Darling, another alternative to the chi-squared test, very high power, really good if you want to detect differences in the tails of your distribution. But because it's so high power, then if you throw a lot of data at it, it's very likely to detect a difference, even when that difference is smaller than you care about. And then the Shapiro-Wilk test, that's one of these ones that's a test of normality, very high power, but is really only good for one thing. So these parametric tests, you often run a Shapiro-Wilk first to see if you're allowed to then use the parametric test that makes the normality assumption. All right, any questions about that? It's just a review of all the stuff we talked about last time. Okay, so then this is something that I had to skip last time, but it does show up at the end of Lab 9 in one of the questions. So you've got this is like your final project. You've picked a system. You decided to you got your input models over here. You've got your decision variables, things that you might play with in the sim, try different amounts of these things over this bank. And then you've got performance variables that you're measuring out here. And there's 3 different performance variables that you could use to see, if I change a decision variable, if I go from 1 teller to 6 tellers, I can look for a difference in performance here, here, or here. And so now the question is, how do I deal with this? That I can look for differences in multiple places. Because there's a problem here when you have the so-called multiple comparisons. You can fish for results that aren't real. So if you were to look for, you could have a group of people who eats peanuts and a group of people who eats jelly beans. And then you could do every medical test you can think of on these people, on these 2 different people. And you eventually might find, so this test, you'll look for differences like, these 2 populations, peanut versus jelly bean, do they differ in cancer risk? Do they differ in hair loss? Do they differ in all these different things? And those are like all of these different things. Do they differ in tellers utilization, average delay, maximum line length? And each one of those tests has an alpha. Each one of those tests has a 5% type 1 error. That means that if you do a lot of these tests, eventually you're going to detect a difference between the 2 populations, but it'll just be due to bad luck. And if you have lots of these tests, then it is very likely you're going to hit one of these bad luck cases. So even though you've got a 5% error rate on each individual output, your family-wise error rate across all of them, like if you're just saying, like, if any one of these medical tests flags a difference, then I'm going to say there is a difference between jelly beans and peanuts. Then in that case, all of those tests together combine into one family of outputs. And you have to consider what's the alpha for that family. And that's the so-called family-wise error rate. And that's the thing you want to be 5%, not 5% for each one of these. Because if you make each one of these 5%, then the probability that you're going to find something by random chance across the family is much, much, much higher than 5%. It might even go to 100%. So how do we deal with that? And the simplest way we deal with that is this way called Bonferroni correction. And here's the idea behind it. So what's the probability of at least one false positive in a group of outputs? Your sims are going to produce multiple outputs. So this is going to be very relevant. You're going to see this on Lab 9. You're going to have multiple outputs that you can use to compare your two sims. And well, the probability of at least one false positive is just 1 minus the probability of no false positives. And so we know the probability of no false positives across all your response variables. It's just 1 minus alpha. And then because there's k tests, k outputs, then that's raised to the k. And so this value here, 1 minus alpha to the k, that is much, much larger than alpha. As alpha gets slightly large, like imagine this alpha is 0.05. Well, that means this 1 minus alpha is 0.95. And then that 0.95 gets multiplied k times. And that 95% times 95% becomes much less than 95%. And that goes on and on and on. So that 1 minus that eventually becomes much, much larger than alpha. So that's the problem with phishing. That's the problem with multiple comparisons. So how do we deal with that? The simplest thing we do is we count how many tests we're going to do. How many comparisons are we going to do? And so that could just be, do we detect a difference in 1, 2, 3 outputs? So that's 3 comparisons. Or if we're saying, is there a difference from population A, B, and C? You might say, well, I'm going to compare population A to B, B to C, and A to C. Well, that's 3 comparisons. So it's however many pairwise comparisons you do, either from an output to like either in one sample analysis where you're saying, does this output differ from 0? Does this output differ from 0? Or 2 sample analyses where does this output differ from this output? Does this output differ from this output? You count up how many comparisons you're going to do. And you, for each individual test, you divide its alpha by that number. So if you have 3 outputs, each individual alpha is not going to be 0.05. It's going to be 0.05 divided by 3. So that's going to make your type 1 error for each individual output much less. It's going to be much harder for you to detect a difference in each individual output. But when you add all those outputs together to say, is there a difference across the family, then that family-wise error rate is going to be close to the 5% that you're actually looking for. Questions about that? That's called Bonferroni correction. There are more sophisticated ways of dealing with this that are outside of the scope of this class, like ANOVAs with so-called post hoc tests, and so on. As you move on, these ones have more power. This is a low-powered version of this correction. If you need more power, you need to use a more sophisticated test. But if you just need to do something quick or you can't find that sophisticated test, this is always a go-to that you can turn to. Any questions about that? Now, often engineers forget to do this because we often don't have a lot of outputs and we tolerate higher alphas. Remember I said in the engineering community, we might be okay with an alpha of 10%. So we might set our alpha in our analysis tool to 5%, but then do a bunch of these, like we might have a sim like this and we do 5% here, 5% here, 5% here, and maybe that will inflate our family-wise error rate to like 15%-ish. But we might be okay with that because again, if we have too many false positives, we're going to follow up with an additional test because we usually are working in a research and development environment where we have extra money to follow good money after bad, but I mean to zoom in on where there might actually be a difference there. So oftentimes, like in the lab question, I actually highlight that the book tells you to do multiple comparisons, but they don't Bonferroni correct, even though the book talks about Bonferroni correction. And I highlight that and I say, hey, actually the alpha should be this other thing. Why? And I'm just telegraphing to the few of you who've shown up, I'm telegraphing to you what the answer to that lab question is. And it's that, it's basically this, is that, we did multiple comparisons, so the alpha needs to be shrunk by that number of comparisons. But oftentimes engineers don't worry about that because we're okay with inflated type 1 error. Other sciences are not okay with that because they do not guarantee that they're going to follow up to check their work afterwards. So they only get one shot. If you only get one shot, your alpha's got to be low. If there's a good chance you're going to follow up, you can tolerate a high alpha. Okay. Questions about that? Good. All right. Good. That's where I wanted you to be going into the homework and that lab. So I want to do a couple introductory things. What we don't get through here, we'll pick up with next time. So new unit. We've talked about the stats. Now that we've got the stats under our belts, what do we measure? How many replications do we use? How do we summarize our outputs? That's kind of what we're focusing on here. And so that brings us to this, and we're talking about sims, these two fundamentally different types of systems that we're going to simulate that cause us to set up our sims differently. Terminating and non-terminating systems, which correspond to transient and steady state simulations. So what are these two different types of sims? Well, a terminating system is like a bank. It has a clear opening in the real world, outside of the sim. In the real world, it has a start. Every replication of the real world has a start point and an end point. The bank opens at 7 a.m., it closes at 6 p.m., and that's it. And so there's no 24/7 operation. It doesn't ever reach steady state, something that I'll talk about in a second here. It's the whole day is just a transient. It opens, you care about everything that happens after it opens until it closes. And then it closes, and then you stop caring about it. And so there is a defined end time, or there is an end time that is defined by some condition that is met in the system. So it might be that you stop the system at exactly 8 hours, or you stop the system when either 8 hours or the queue length after 8 hours goes to 0. So it might be that you allow for, like, anybody who's in the bank at 6 p.m. gets to have their service, gets to get their service, but they lock the doors behind the people at that point. So nobody can arrive after 6 p.m., but because there's people in the queue, then the bank might not actually close or finish until 6:30 p.m. And so you might need to record the actual end time as a random variable. That might be one of your outputs, is that how often do we actually end at 6 p.m. that day? So that's our idea of a terminating system. And we often simulate it by a transient simulation. So a transient simulation, as we'll see, is a sim where we care about all of the data. So you set up the initial conditions. The initial condition has to be perfect. It has to match the real system. You hit go, and then you collect data from the entire run until that replication ends. And that's your whole replication. You don't throw anything out. And you'll see what I mean by throwing things out when we talk about the other half of this, the other type of system. So I gave the bank example there. Inside Arena, this is from the old version of Arena, but it's the same idea in the run setup. There is, you set your number of replications on these transient simulations. That's another thing, is that you will, in a transient simulation, you're almost always going to run more than one replication, because it's going to be about how many reps. Like, so we're going to see with steady state simulations, there are tricks we can do where we only need to run one replication. But for transient, we need to run multiple. And there's a terminating condition. So either we end at a particular replication length, which is up here. This one's set for infinite because here, in this particular setup, this call center setup, they have a situation like I was talking about at the bank, where they say, we're either going to terminate when we only terminate when we reached a particular time of day and when there's no one left in the queue waiting for service. And so sometimes they'll end right at 600, whatever this is, minutes. Other times they'll end a little later than that because they have to wait for that queue to empty. So that's what I mean by terminating system and a transient simulation. Any questions on those? Okay, so The other side of that, non-terminating system runs for a relatively long period of time, essentially continuously. Like a 24/7 grocery store or Walmart, at one point they had to, they had to open the store. But for most of the operations of that store, that we just consider it as being just going. And so we don't want to focus our optimization effort on that few hours of that weird time where the store was closed and it, for renovations or whatever. We just assume that eventually those effects will die out. And what we focus on is not what's happening when they open, but what they happen when they're continuously running. At the bank, you really do care. Every morning, there are people lined up at the bank trying to get in. So you do care about the start of those systems. But for a non-terminating system, we admit that there probably was a start of the system, but the thing that we as the operations researcher are focusing on is something so far from the start of the system that we can ignore that it ever happened. And so that's what we mean by a non-terminating system. It runs for a very long time. And we use a different type of simulation for that. We use a steady state simulation. So this is to try to analyze the long run properties of the simulation. So our sim has got initial conditions. And what we're going to talk about in this unit or in this lecture and in the next lecture is how to reduce the effect of our choices of initial conditions on the steady state estimates. Because the steady state estimates should be independent of whatever we've done initially in this sim, because the initial conditions of our sim don't mean anything to our stakeholders. Our stakeholders only care about the long run behavior. So if our estimate of the long run behavior is conditioned on the initial conditions in our simulated world, then we've done something wrong. So that's what I mean by a steady state simulation. We are ignoring the initial conditions. So we don't have an end time that corresponds to the real world, but we can't run our sim forever. So we will have an end time in the sim, but we have to be clever enough to do something special with our initial conditions in the sim and run our sim for long enough so that our finite sim is a good approximation for the infinite real system. That's the key to how you set up these steady state simulations. And that's what we're going to be talking about in this unit. How to figure out the initial conditions to make that happen and the stopping time to make that happen. So assembly lines that basically run all the time, like Amazon, Amazon's distribution system, it's running all the time. You order something in the middle of the night, you get an email 30 minutes later saying it's already out for shipping. That's what we mean. Those types of systems we're analyzing right here. We can summarize these two systems in this diagram here, where we've got the transient the transient sim that is simulating the terminating system. Here, we care about all of the data. So here, this is the natural start time of the real system. It rises up. There maybe is some interesting dynamics that happen throughout the day, and then it ends at a natural end time. And we care about so the estimated time in the system is affected by the stuff that happened in the morning, as well as stuff that happened in the afternoon. That's why this estimated average is pulled down, and that's the right output, because it's affected by both of those. We had real customers in the morning that had a very different experience than real customers in the afternoon. We care about both of those customers, so we use all of the data. The same graph, but now we envision it as a non-terminating system with a steady state simulation. Here, this initial part, this is something that doesn't exist in the real world, but it had to exist because we had to hit play in Arena. And so we had to start somewhere. And so this is where we chose to start in Arena. And Arena ramped up as if it was one of these systems over here. And so this ramp up that's in Arena, we need to get rid of that. That's the so-called warm-up period. And so we need to warm the system up, and then only after the system is warmed up, then we start taking data. So the idea here is that if we didn't warm the system up and throw away this data, then we would get this estimated time in system here. But we don't care about these customers. These customers are fake customers. They don't exist in the real world. They're just there to warm our system up. And once our system's warmed up, then we start caring about the customers that come after that. So really, we should have an average which is somewhere in the middle of these squiggles, which is up here, not this average down here. And the difference between those is something we refer to as bias. So in steady state sims, our choices of our initial conditions and how long we're going to run our sim affect the so-called bias in our estimates. And we need to try to minimize bias. All right, questions about these two pictures? We'll see those pictures several times throughout this unit. Okay. All right, so I'm just gonna capture a couple other things here so that we're in good shape for the next lecture. This is some examples here from multiple replications. So we've run 3 different replications of a sim. And so, and then in each replication, we're going to do something called batching. What is a batch? A batch is for a long sequence of data, and this applies to machine learning. So everybody wants AI in their degree right now. And so when you're training an AI algorithm, you often use batching, and it's the exact same thing. So if you have a data set, a big data set, a lot of data here, if you create smaller groups of data, those are the things, those are referred to as batches. So we're saying that for every replication, we created 5 batches. So that's why we have 5 numbers in this replication. There's actually 5,000 minutes of simulation data, but batch 1 is the first 1,000, the second 1,000 batch 2, and so on. So we can now take data, take stats on the batches. So we can say, what is the average output just for this batch? And then we get 5 averages per 1 replication. So that is, we can do that across all 3 of our replications. And when we do that, we see certain things. So for one, I see that this replication so all 3 of these replications are independent from each other. I cannot predict numbers in this replication from numbers in this replication. So there's a lot of diversity across replications, and we can count on that. That's why we use different random number seeds to generate each one of these replications. And that guarantees that numbers from one do not allow you to predict the other. But within the batches, you get a lot more predictability, or within the replications. So here I noticed that replication 1, these are all relatively small numbers, even though big numbers are apparently possible. So there's something that happened in this replication that is a connecting thread that is going through the entire replication. And this tells me, if I look at the variance across replications and within this replication, that I cannot trust that these batches as to be independent. Because if these batches were big enough to be independent, I should see the same variance down the batches as I see across the replications, and I don't. So there's very little variance across the batches, even though there's a lot of variance across the replications. So there's correlation, there's autocorrelation. So that's a common thing, autocorrelation within a replication. It can show up in different ways. In replication 2, I see a pattern where this almost suggests a warm-up period that needed to be thrown out. So this was at the start of this sim, you had very little waiting time because there was nobody in the line, because the bank just opened and it was empty. And as people start filling the bank, eventually you reach a steady state, and the steady state might be this up here, but then these are that warm-up period. So you see this continuous ramp up, and that is also autocorrelation. And then you get a very different pattern here. So maybe this one doesn't have autocorrelation. So if all of my replications looked like this, if all of my batches looked like this, then that would tell me that maybe if I'm doing a steady state sim, I only need to run 1 replication, and I can just cut things up into batches and treat every batch as a replication. And that means I don't have to worry about more than 1 warm-up. These are the things we're going to be getting into. So this picture here of variation within a replication and variation across replications. Those are the key things that we're worried about in this unit. All right, any questions about the data that's up there, or this idea of batches? Okay, so with that, cross-replication data, we're going to assume to be independent, identically distributed, and often normally distributed. This is why I don't make you do normality tests in this class, because in most of the sims that we run, the data we get out of a replication is actually the sum of a bunch of things, and they tend to be normally distributed. So if I did make you do a normality test, they almost always would pass. That's why we don't worry about it here. That isn't always the case. But so across replication data meet the assumptions of our statistical tests, of our parametric tests, of our t-tests, of our ANOVAs, and so on. But across the replication data, then we are often going to summarize with sample mean. So we're just going to take the average across all our replications. Notice I'm using capital R. That's my number of replications. So sometimes I'll use N to be the data within a replication, little n, and then R to be the number of replications. So this is summarized. This is taking the sum across replications. That's why I've got the capital R. And so because they're independent, I can use standard error of the mean. So if you remember when we derived standard error of the mean a couple lectures ago, I said this formula relies on the data being independent. So, and they are independent across replications, just not within. So I can take this standard error of the mean, and that calculates the spread of the mean, not the spread of the data. So every time you run your sim, every time you run 10 replications of your sim, you'll get one mean, another 10 replications, another mean, another 10 replications, another mean. And this is the spread of the means, not the spread of the sim. Standard error of the mean. So that'll be an important quantity. And then down here as your number of data in your standard error of the mean, I guess I should have put that as a capital R instead of an N there. As that number gets higher, the standard error will get smaller. So if you go from 10 replications to 10,000 replications, then every 10,000 replications is going to generate a mean that'll be very similar to the last 10,000 replications. But if you're only running 10 replications, then every time you generate a mean, you'll get a different mean than the last 10 replications. That's what's being captured there. And then within replication data, we don't have any of that. So we're not going to be able to run t-tests and all that from within replication data unless we do a bunch of extra work. So generally speaking, within a replication, the samples from within a replication, one customer's waiting time, the next customer's waiting time, and so on, will be auto-correlated. If one customer waited for 5 minutes, the next customer is probably going to wait for close to 5 minutes, even if a customer 100 down the line only waits for 2 minutes. Their experiences are often locally correlated. So that's why we can't treat them as independent samples. So we can't use standard error, we can't use t-tests, and so on from within a replication. So, and that's all I'm sort of saying here. And you know, I gave the already kind of examples of this where you've got autocorrelation within here, which means that you can't treat these as independent replications. You can only go across replication there. And then this is the last thing, and then I'll let you go. And then I already hinted at this. This idea of initialization in steady state simulations opens up the problem of bias. If we do not do a good job cutting off that warm-up period, then our estimate of performance will be corrupted by data in the warm-up period, which has no relationship to the real world. And that introduces a difference in the mean of our estimator and the real mean in the real world. And the difference between those two means is what is defined in statistics as bias. And that's what we'll pick up next time. So let me just get to one of these clickers. All right, so then the question I have for you is, what is the term that represents the difference between the mean of your estimator and the mean in the real world? So your estimator, if you run your sim multiple times during multiple estimates and take the average of those estimates, that will sometimes differ from the real world average you're trying to represent. That difference between that, what is that called? What's the statistical term for that? And that's all I've got for you. So then we'll see you Thursday.